Let me welcome you to this lecture. We have been discussing the symmetry selection rules in cyclization reaction, and we have so far talked about the selection rule for dimerization of olefin, and we have seen from both orbital correlation diagram as well as from the correlation diagram of electronic states in the reactants as well as in the products in this dimerization of ethylene reaction, and we found out that this reaction is thermally forbidden, but it is photochemically allowed, and also experimental data also support this particular fact, and this essentially shows how good or how successful these symmetry selection rules are in predicting the outcome of a reaction. Now let us proceed further and then discuss symmetry selection rules for another very important type of cyclization reaction, that is the 4n+2 cycloaddition reaction, or the Diels Alder reaction. So we know about the Diels Alder reaction already, that it is, you can take a diene and it reacts with an olefin to give us a cyclized product. In this case, the product is going to be again a monoolefin in this way. So we'll do symmetry analysis of this particular reaction, and for that, first what we'll have to do is to find out which symmetry elements or persist during this concerted reaction, and then we can find out, or we can do symmetry analysis of the orbitals involved in reactants as well as in case of the product, to correlate the bonding and anti-bonding orbitals in the reactants and the products, and from there we can find out the symmetry selection rules for this reaction. So in order to find out which the symmetry elements persist during this concerted reaction, we have to see, or we have to visualize how the two reactants come close to each other and which orbitals of the reactants essentially interact with each other. So this is, this can be made easier if we place the reactants on two perpendicular, two parallel surfaces of a cube. So let us draw that. Let us draw a cube. So this is how we have a cube here, and so let us place the olefin, that is the olefin, on the top surface of the cube over here, and then we can place the diene here on the bottom surface of the cube here, and that is how the olefin and the diene approach each other while during this 4n+2 or 4+2 cycloaddition reaction, or the Diels Alder reaction. So now if we find out what symmetry elements are going to persist during this reaction, what we will find is that only one symmetry operation, that is this one plane of symmetry, which bisects essentially the double bond in the olefin and the single bond in case of this conjugated diene. That plane of symmetry is the only symmetry element which persists during this reaction, during this concerted process, and we will have to identify whether the orbitals involved in this reaction or the orbitals in the product are whether symmetric or antisymmetric with respect to this particular plane of symmetry. So we now know how this plane of symmetry orients itself with respect to the approaching reactants as well as with respect to the product. In the case of the product, the plane of symmetry bisects the product in this way, as well as here also it bisects the olefin in this way, the plane of symmetry, and it bisects the diene in this particular fashion. So let us draw the orbitals in the reacting system as well as draw the orbitals in the product to find out whether these orbitals are symmetric or antisymmetric with respect to this plane of symmetry. So if an orbital is going to be symmetric with respect to this plane of symmetry, then the wave function associated with that orbital, we will denote it as A type of wave function, symmetric with respect to the plane, and if it is antisymmetric, then we will denote it as B type of wave function. So then let's draw the molecular orbitals of these 9 which are going to participate in formation of the during this Diels Alder reaction. What we see is that the double bond here in case of the diene are essentially converted into, because if I level this as 1, 2, 3, 4 and then 5 and 6, then what we see that this is 1, 2, 3, 4, 5 and 6. So what we see is that the double bond that was there in between atom number carbon 1 and 2 and 3 and 4, they are converted into single bonds. So the p orbitals involved in formation of double bond, or the p orbitals on atom number 1 and carbon 4, here they go on to form sigma bonds with the p orbitals, which form the pi bond, p pi bond, in case of this olefin, that is with atom number 5 and 6. So these 4 p orbitals, which are initially participate in pi bonding in case of the reactant, they get transformed into sigma bond orbitals. So we will look at the symmetry of these orbitals, or we'll do symmetry analysis of these orbitals with respect to these plane of symmetry. So let's draw these pi bond molecular orbitals of this butadiene first, and we will draw the molecular orbitals with respect to the energy here. There are going to be 4 molecular orbitals for the butadiene. So first is the bonding molecular orbital, where all the p orbitals are in phase, and so if we put them as plus and minus instead of dashed lines here, so if we do find out whether it is symmetric or antisymmetric with respect to this plane of symmetry. Now, the plane of symmetry passes through the butadiene in this way, through the central CC single bond here. So we see that it is symmetric with respect to the CC single bond, and that is why we can label this as psi A. This particular wave function, we can label it as psi A because it is symmetric with respect to the sigma. Then let us draw the next molecular orbital, which has one node in this way. So that is, if we see now, this is psi B because it is antisymmetric with respect to the sigma. Then we have molecular orbital with 2 nodes, and in this case again what we see is that this is symmetric with respect to the sigma over here, and the last one is completely antibonding molecular orbital of butadiene, and this is again antisymmetric with respect to the sigma plane over here. Then we see the molecular orbital of the p-pi molecular orbital of this reactant or diene or this olefin over here. So in this case, there are only two molecular orbitals. One is the bonding and the other one is anti-bonding. The bonding molecular orbital and anti-bonding molecular orbital. So this is with respect to the sigma, it is psi A, and with respect to the sigma, this anti-bonding molecular orbital is going to be psi B, and symmetric it is. So now let us, because we need to identify these molecular orbitals as molecular orbitals from the olefin. So that is why let us put a plus sign over here, so we can distinguish these molecular orbitals from the molecular orbitals of the diene. Now let us draw the molecular orbitals of, or what we can do is we can draw these molecular orbitals of the the uh, the product formed after this Diels Alder reaction here. And for these, again, we have two sets of orbital to be drawn, or the new bonds that are formed here are the sigma bonds. Two sigma bonds are formed, and one pi bond is formed between C2 and C3. So we have two sets of orbital once again, and the sigma bonds, you see, if we draw here, there are going to be four molecular orbitals again. So this is completely bonding here. All the lobes are in phase here. And then we have bonding here, sigma bond, but in case of the pi here, it is anti-bonding. That is why this will have higher energy than this particular molecular orbital here. Then we have anti-bonding orbitals, sigma orbitals, and then we have completely anti-bonding, that is in this way. So that is the another molecular orbital. So let us now again find out the symmetry of these sigma molecular orbitals of the product. So with respect to the plane of symmetry, which bisects the product in this way over here, so that we will find out this is symmetry with respect to the plane of symmetry. So we level it as psi A sigma, and then we call it again. This one is also, this is antisymmetric. So psi B sigma here, and this is symmetric, psi A sigma, and this one is psi B sigma. So we see these are the bonding molecular orbitals, and these are the anti-bonding sigma anti-bonding molecular orbitals in the product. And now also for the pi molecular orbital, we can draw these pi molecular orbitals in the product. This is the pi bonding molecular orbital, and then we have also the pi anti-bonding molecular orbital in the product. in this way, and this is psi A pi, and this is psi B pi, because it is antisymmetric with respect to the sigma. So we have identified the all the molecular orbitals or symmetry of all the molecular orbitals in in the reactants as well as in case of the product. Now we will draw the orbital correlation diagram, and for that we have to draw the energy of these molecular orbitals, which is in order of their energy, and then we will also have to distinguish between bonding and anti-bonding molecular orbitals. So we see that these are the bonding molecular orbitals in butadiene, and these are both occupied molecular orbitals in case of butadiene. So we see that these are the molecular orbitals, that is psi A1 is completely filled, again psi A is completely filled, psi B is also completely filled, and these two molecular orbitals, which are antibonding antibonding molecular orbitals of butadiene, they are empty. Again, what we see is that for the reactant here, these two molecular orbitals, this bonding molecular orbital of the olefin here is completely filled, and this antibonding molecular orbital of the olefin here is empty over here. So we write these here. Let's write it as psi B plus, and let's write it as psi A plus. Now, when we write or when we draw the molecular orbitals on the sigma molecular orbitals on that is psi A sigma of the product, psi B sigma of the product, then we have psi A pi of the product, and then we have the antibonding psi A sigma and psi B pi and psi B sigma, antibonding sigma molecular orbital in the product. So these are the, we have now drawn the energy or the molecular orbitals, which is in order of their energy, and these two molecular orbitals we see, or these three molecular orbitals in the product, are all occupied molecular orbitals here, and what we see from here is that we can correlate the molecular bonding molecular orbitals of same symmetry with bonding molecular orbitals of same symmetry in case of the product here. So that is the psi A gets converted to psi A sigma here, and then the psi B sigma psi B here gets converted into psi B sigma, and then the psi A plus gets converted into psi A pi over here, and then again this is how we can correlate the energy of this is going to be more because it is sigma antibonding molecular orbital. So psi A sigma and then psi B pi. So this is how we can correlate these molecular orbitals, the antibonding molecular orbitals in this way. So what we see, or what we are out, this is the orbital correlation diagram for the Diels Alder reaction, and what we see from here is that all the molecular orbitals, bonding molecular orbitals in the reactants correlate with the bonding molecular orbitals in the product, and all the antibonding molecular orbitals in the reactants essentially correlate with the antibonding molecular orbitals in the product and the field, because the bonding molecular orbitals are filled, and that is why these molecular orbitals, they get transformed into the bonding molecular orbitals or field bonding molecular orbitals of the product without any change in symmetry. And that is the reason, because we can correlate the bonding molecular orbitals with the antibonding bonding molecular orbitals in the reactants with the bonding molecular orbitals in the product. This particular reaction, that is the Diels Alder reaction, is essentially can proceed in the ground state itself, and the reaction is, that is why, allowed thermally. And of course, experimentally also it has been observed that the Diels Alder reaction proceeds on heating, or at times, for specific substrates, the reaction proceeds even at 0 degrees Celsius. That is possible because the conversion of the reactants to the products is possible in the ground electronic state of the reacting system itself. So this is essentially the symmetry selection rule for the 4+2 cycloaddition reaction by using this Woodward-Hoffman rule. So this essentially brings us to the end of this lecture. What we have learned during this lecture is how we can do symmetry analysis for a 4+2 cycloaddition reaction. And what we did is that we identified the symmetry element which persisted during the entire course of this concerted reaction. Next, what we did is that we analyzed the symmetry of the participating orbitals, that is orbitals of the reacting system as well as orbitals in the product with respect to the symmetry operation that persisted during this course of this reaction, which is a plane of symmetry which bisects the sigma bond in the diene and the double bond here in case of the olefin, and also the double bond in case of the product formed over here. And then what we did is that we correlated the orbitals in the reacting system with the orbitals in the product here with respect to the symmetry, and then we found that the molecular orbitals in the reacting system, or bonding molecular orbitals in the reacting system, essentially correlate with the bonding molecular orbitals in the product, and that allows us to predict that this reaction can proceed in the ground electronic state itself, and that is why it should be allowed thermally. So that is how we could arrive at this Woodward-Hoffman rule or law for this Diels Alder reaction. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.